Okay, so now we are in the middle of proving Hajnal-Szemeredi theorem. And what we have shown, we show that if you have a minimum counter example G, then that has a nearly equitable K-coloring, where the one part has size R minus 1, and then one part has size R plus 1, and every color class, other color class has exactly size R. And then we consider this accessible color classes and inaccessible color classes. And among accessible, you choose the ones they are free and not free. In short, accessible ones are the ones that you have a vertex. You keep sending it until you send it to V1, the smaller color class. And free ones are the ones that does not block anything. So even if you make some changes here, then everything else is still accessible. And then we show that we show that in this choice, there are no solo edges with the X being movable. That's what we showed. Here, solo edge is the edge that this vertex sends has no other neighbors but this. And movable means that there is another color class that this vertex does not have a neighbor, so you can move. And when this belongs to the pre-accessible class. And also we show that there is no case that there are two solo edges sharing same vertex X, and X is non-movable. And this Y and Y prime are non-adjacent. Now we want to show is that one of the two situations that the above two claims describe must happen. So by this claim, it suffices to find the solo edge with its endpoint in A prime is movable, or two solo edges having a common neighbor, common endpoint in A prime whose other endpoints are not adjacent. So let's consider two cases. So first case is where A prime is at most B. So recall that A prime is the number of free accessible classes, and B is the number of inaccessible classes. Assume that the V2 to VA minus A prime, they are not free. They have a roll indexed out neighbor in DF. So we can assume that by reindexing. Then the set VA minus A prime, which is the last one which is not free, that blocks some class VJ. So that's not free, that means it blocks some case, some class which is still accessible. Then what? Then for each X in this VJ, we have that the number of neighbors of it in A is at least A minus A prime minus 1, as this X is not movable to any VI which is smaller than A minus A prime. Because this last one blocks it. That means X cannot be moved to any of the earlier class. If this can be moved to here, then this, even without this, you can find the path in D super F, D superscript F that reaches B1. So contradiction, that means this cannot be moved to any one of these, can be only moved to here. That means it has a neighbor in everything else in the earlier one. So this is not movable to any previous one, so you know this. Hence, the number of neighbors of this in B is at most k minus what? A minus A prime, which is like B plus A prime, and that's at most 2B. Okay, now we consider this Bj, and then you partition it into U and U prime. And then what's U? U is the vertices there, and that is incident with some solo edge. And U prime are the remaining one. So we have an upper bound on here into this B, BA plus 1, BA plus 2, BK. So let M be the number of edges between U prime and B. Then what do you know? M is at most. So you have this upper bound on the number of edges, so 2B times U prime. On the other hand, we know that these classes are not accessible. So every vertex here has at least one neighbor in Bj. Because if this one doesn't have a neighbor, then you can move it to here, making this accessible. This is accessible, and then if there are one vertex you can move, then this is also accessible. So we know that every vertex for B has a neighbor in Bj. Like B prime, which is subset of B, is the set of vertices Y, which is an endpoint of solo edge xy with some x in U. Then what do you know? Then the vertices in B minus B prime, we know that all vertices in B have at least one neighbor in Bj. But it's not in B prime means that that edge is not solo edge. So it's sending another edge. So this have at least two neighbors. And those two neighbors are all to U prime because this is not solo edge. Give me a moment. Okay, let's change the definition of this B prime a bit. So instead of that, let's take B prime is neighborhood of is U in B. Okay, let's go. Then what? Then the vertices in B, but not in this B prime, they all send at least one edge to Bj, but the descendant edge to U prime, because B prime, it's not in B prime. So if some vertex sends an edge to U, then that must be in B prime. So these all have a sending to U prime. But again, this one is not solo edge, meaning that this has another edge sending, but that also should lies in U prime. So it has at least two neighbors in U prime. So what we do? Number of edges is at least 2 times the B minus B prime. So now what we know? If you compute this, so R times B is what? R is same as size of U plus size of U prime. That's R. Then you plug that in, then that's B times U prime plus B times U plus A minus 1 times U. That's A plus B minus 1 times U. It's K minus 1 times U. And what do we know? We know that the number of edges M is at most 2B times U prime. So it means B times U prime is at least M over 2. And you know that all the vertices in U has degree at most K plus 1. So you can write it this way as a lower bound. And from here, M over 2 is at least size of B minus size of B prime. And for this, what do you have? Each vertex in U sends at least one. So you have say B here, it sends some edges. And A here, it sends some edges. You add all of them. So for this part, that's lower bound. So how do you count this? So you count the number of neighbors in A, and you simply add this B prime here. And that's the lower bound. Because for the number of edges between here and here, so this part is what? From here to here. This is number of edges between A and U. And this is number of edges between U and B. But between U and B, what? For each vertex in B prime is the neighborhood, any vertex that has at least one neighbor in B. So for each vertex, you count that, and that forms a lower bound on here. So you have this. So this together is a lower bound on here, because this is lower bound on here. And what? You have a B, and then this cancels out. And size of B is what? BR plus 1. And for all vertices in U, you add degrees towards A. And from here, what you know? A minus 1 times U is bigger than the summation of all say degrees towards A plus 1. Then, so you just subtract it. That means what? You add all the degrees of the vertices in U, and then it's smaller than A times 1, A minus 1 times U. Then there must exist a vertex X in U with standing, has a less than A minus 1 neighbors in A. But that means that out of this B1 to BA, and then U belong to what? Pj. So except that there are a-1 classes, and then it's sending less than a-1, so at least one of them is, this vertex does not send any edges. So this X is movable. And X is movable and it belongs to U, means that there is a solo edge here. That's the definition of U. So that's as we desired. So case 1 is done, and you consider case 2. Case 2 is where P is at most A prime. Then what? Now we take a maximum independent set I in B. Then what we know? Then we know that this I has size at least R. Okay? So in fact R plus 1 because P sub K has a bigger size. And what we know is for each Y in B, we let sigma Y be the number of solo edges incident to Y. So here we want to find the case that the two solo edges sharing one vertex in here. So we want to we want to show that the sum two solo edges collides in one of the free accessible class. For that, let's say for each vertex, you count the number of solo edges incident to Y. Then what? You consider the number of neighbors in Y in A, and that's at least A plus A prime minus sigma of Y. Why? I mean, because this is inaccessible, so Y belongs to the inaccessible class. That means Y sends at least one edge to every one of these. And when this is the free accessible one, let's say this is the free accessible. If this sends only this edge, then this becomes solo edge. Okay? But out of this many is not solo edge. This is not solo edge. This is not solo edge. Then for each not solo edge, there must be another one. So you have to add this much on here, the number of edges from this towards A. Thus, what? From here, what we get? You move this term to here, then this is at least A plus A prime minus the number of neighbors in here. And we assume that the B is less than A prime. And this is what? At most, this is at most K minus 1 minus number of neighbors in B. And that's like A prime minus P plus 1 minus the number of neighbors of Y in B. Okay, so we know this. And as we take I as maximal one, we know that for all the vertices in Y, if you add the neighborhood of y, the number of neighbors of y in B plus 1. So 1 is counting the vertices in y itself. So we count the close neighborhood for each one of them. And that covers everything. So that has size at least B. Otherwise, it's not maximal, then you can add one more vertex. This has size at least BR plus 1. Then what do you know? From here and here, you take the all vertices in I, and then you add sigma B. Then using this is like A prime minus D plus the number of neighbors in B plus 1. And the size of I times A prime minus B. And for all Y, you add the number of neighbors in P plus 1, which is at least size of B, which is BR plus 1. And we know that this extremal independence has a size at least R. Then you have this. This size is bigger than A prime. And what does it mean? So this sigma I counts the number of solo edges ascending from this Y to some vertex in A prime. But the number of edges is bigger than A prime. That means there must be one edge, one vertex here receiving two such things. So there are two solo edges. Both arrive in this A prime. And they are not independent. They are not adjacent because they belong to the independent set. Again, if this is movable, then you are done by the first claim. So you have one solo edge, this is movable, and we are done. If it's not movable, then there are two solo edges, and then they are not adjacent. This is not movable. That means the second claim says that we found what we want, and the second claim says that you can't get the contradiction to our choice of F, which is the nearly repeatable K coloring with the largest number of accessible classes. So this is we obtained two solo edges sharing common vertex in A prime as desired. So this proves the Hajnal-Szemeredi theorem as we want. Okay, so yeah, there are a bit more things that I want to talk about, but maybe we do it in the next video. Okay, thank you for listening. I will see you in the next video then.